Hey, what's up, Chem Leads? This is a very bittersweet moment because this is our last lesson in chemistry. So I want you guys to give yourselves a pat on the back because I am so proud of you guys. You have persevered through this challenging year for so many different reasons, and you are very well equipped to go on to physics next year, which is going to be combining English, math, and science all into one subject. So I hope you guys had a great time in chemistry. I hope you learned a lot. And we're going to be finishing out strong with our last topic on thermo. So let's spend some time talking about our agenda for today. So we're going to be first talking about the laws of thermodynamics. Then we're going to be talking about temperature. And we're going to be moving into the bulk of the lesson, which will be on heat. And the important thing is to know that heat is different from temperature. And then after we talk about heat, we're going to be talking about calorimetry, which is when we mix substances together. So let's begin with our objective. So students will calculate the amount of heat required for a temperature change and the final temperature when mixing two substances together by analyzing the math model Q equals MCAT, or MC delta T. Now, the common name for this equation is Q equals MCAT. So you guys are probably wondering, what the heck is thermodynamics? Well, thermo means heat, and dynamics means changing. So thermodynamics is the study of energy transformations involving heat, work, and other aspects of energy, and how these transformations can relate to the properties of matter. So for instance, we're going to be talking about how when you heat something up or take heat away from something, what happens to the matter? Does it change? So we're going to be talking about that. So, and we care so much about thermodynamics because it's so important in different science classes such as biology or life sciences, chemistry, and physics, which you'll see next year. And it's also important because we use thermodynamics for a lot of real world applications such as car engines, refrigerators, biochemical processes, chemical reactions, and the structure of stars. Now let's learn the laws of thermodynamics. There's four of them. But the first one's not actually called the first law of thermodynamics. The first law is called the zeroth law of thermodynamics. And what this means is that two or more bodies in thermal equilibrium have the same temperature. So, if object A and object B are in thermal equilibrium, they have the same temperature. If object A and object C is in thermal equilibrium, they have the same temperature. If object A, B, and C are all in thermal equilibrium, they all have the same temperature. So the zeroth law just says that if you're at thermal equilibrium, you have the same temperature. The first law of thermodynamics says energy is conserved and cannot be created nor destroyed, only transformed. And you guys already know this. It's called the conservation of energy. And that's the first law of thermodynamics. The second law of thermodynamics is entropy, which is disorder. So, disorder in the universe must increase in every spontaneous reaction. Heat cannot move from a cold body to a hot body. So, the second law of thermodynamics says that heat always goes from hot to cold, not from cold to hot. All right, and that's the key point. You're going to unpack this law next year in Physics 1. The third law of thermodynamics says that as you approach absolute zero, which is Kelvin equals zero, the entropy approaches a constant value, which is zero for solids. So the third law says that the lowest temperature you can ever get is 0 degrees Kelvin, or 0 Kelvin, which is absolute zero. And again, you're going to be unpacking this one more in Physics 1. So here are the three laws again. The zeroth law, when you're at thermal equilibrium, you have the same temperature. The first law, energy is conserved and cannot be created nor destroyed. The second law, heat goes from hot to cold, not from cold to hot. And then the third law, which is the lowest temperature you can have is 0 Kelvin. Now, let's talk about what temperature is. You guys have all measured your temperature before. You probably even measured your temperature even more now with COVID-19 going around. So, what is temperature? So, temperature is a qualitative hot or cold. That's all it is. Is your temperature hot? Is your temperature cold? So, and many things we measure depend on temperature. For instance, like if you have a fever. So, some areas where we measure temperature could be the length or the volume of materials. Just like in the summertime, your doors are harder to open in your house because they swell up. A second area we measure temperature is when we're measuring the conductivity of a wire. The third place we can measure temperature is when we're looking at the color of hot objects. We know that a blue flame is hotter than a red flame. And the fourth area we can measure temperature is when you're trying to figure out what you're going to wear for the day. You know, if it's a hot day, you're not going to wear a coat outside. If it's a cold day, you're not going to be wearing flip-flops and a tank top. So understanding temperature is really important. But the key thing is temperature is related to molecular motion. So as you guys know, we have different temperature scales. So to use temperature as a measure of hotness or coldness, we need a scale. A device used to measure the temperature is called a thermometer. And we can use length, pressure, and resistance to make a thermometer. I'm not going to go through the science of how a thermometer works, but if you're in Physics 1 next year, maybe I'll explain it to you then. So here are our three scales for temperature. We have the Celsius scale, then we have the Fahrenheit scale, which is a little bit higher than the Celsius scale. And we have the Kelvin scale. And if we want to switch between these three scales, we have three equations. So if we want to go from Celsius to Fahrenheit, we use that first equation. So the Fahrenheit will be equal to 9/5 the Celsius temperature plus 32. The next equation is going to give us the Celsius temperature. And then the last equation will give us the Kelvin temperature. Now, we need to understand how to convert one because some chemistry and physics problems will require you to. But also, in the US, we use Fahrenheit a lot. But all across the world, they use Celsius. So the US is very unique. I don't know why our measuring systems are different, but it's important that we understand how to go between them just in case we need to in the future. So let's do some practice problems. So at the top, I have the three equations. So the first question says go from 3 degrees Fahrenheit to Celsius. So if I'm looking for Celsius, I'm going to use that middle equation where I plug the 3 degrees in for F. The second one says 39 degrees Celsius to Fahrenheit. So to go from Celsius to Fahrenheit, I use the first equation. The Fahrenheit temperature will be equal to this, and we'll get 102.2. Notice how 39 degrees Celsius is equivalent to 102.2 degrees Fahrenheit. 102.2 is higher than 39. Remember I told you that the Fahrenheit temperature will always be a little bit higher. Now, the third one says to go from Kelvin to Fahrenheit. So 295.92 Kelvin to Fahrenheit. Now, this one is a two-step question because I have to go from Kelvin to Celsius and then Celsius to Fahrenheit. So to go from Celsius to Fahrenheit, I subtract that. I do 273 minus that temperature. And then I'll be in Celsius. And then to go to Fahrenheit, I'm going to use the red equation. And I get that 295.92 Kelvin is equal to negative 9.26 degrees Fahrenheit. Now, some of you guys might be wondering that equation I have in green for this question is a little bit different than at the top. The reason for that is I rearranged it to get Celsius. That equation at the top is for Kelvin, but if I want to get Celsius, I just subtracted 273. All right. Now, the fourth question says 72.4 degrees Fahrenheit to degrees Celsius. So I'm going to use the blue equation because I want Celsius. And I'll get 22.4. Notice how the Celsius temperature is lower. The fifth question says 350 degrees Fahrenheit to Kelvin. This is another two-step question. I have to go from Fahrenheit to Celsius and then from Celsius to Kelvin. So let's first go to Celsius. And now that I'm in Celsius, I can add 273 to get to Kelvin. And then, last but not least, 20 degrees Celsius to Kelvin, which is the easiest one. I just add 273, and I get 298 Kelvin. Now, if you still do need some help with temperature conversions, because I did go through those pretty quickly since I'm pretty sure you learned them in biology, here's a temperature conversions Kahoot that you can do. I'm not going to be grading it, but this could be extra practice if you want some help. So, now let's talk about heat. So, the quantity of heat. And I have a Q right there because heat has the symbol Q. It's not H. Because next year, or in 2 years in Chemistry 2, you'll learn what H is. But Q is heat. Let's revisit the zeroth law of thermodynamics. The zeroth law of thermodynamics said, when two objects are in thermal equilibrium, there is no heat transfer, and the objects are at the same temperature. So when they're at thermal equilibrium, nothing's going to lose heat, nothing's going to gain heat because they're in equilibrium. Alright, so if two objects are in thermal equilibrium with a third object, then they are all in thermal equilibrium with each other. Note that anytime we use a thermometer, we're using the zeroth law of thermodynamics. Because when you stick a thermometer in something, that thermometer reaches thermal equilibrium, and it will rise and fall based on when it reaches that thermal equilibrium. So, what's the difference between temperature and heat? Well, temperature is a qualitative or quantitative description of the hotness or coldness of objects based on how fast the particles move. Hotter objects have faster moving particles. Colder objects have slower moving molecules or particles in it. All right? So, temperature, just think of it as it's hot, it's cold. That's all it measures. But heat is the energy transfer from one system or one object to another system or objects because of a temperature difference. So if I put something hot next to something cold, there's going to be energy that moves from the hot object to the cold object because it has a temperature difference. Now this is super important because when things have a temperature difference or they're at different temperatures, there will be heat transfer until it reaches equilibrium. When it reaches equilibrium, remember they have the same temperature and there will not be heat transfer. Alright, so the key difference is temperature is hot or cold, heat is the transfer of energy because of a temperature difference. Since heat is directional, it can have two signs. If you have a positive Q, that means heat is entering into a system. That means you're heating something up. If heat is negative, so you have negative Q, that means heat is leaving the system. So it's giving off heat. So positive Q, you give it heat. Negative Q, it releases heat. And the unit for heat is joules. So, as an example, when you put a hot spoon in a cold cup of water, two things happen. The spoon will cool down. That hot spoon is going to cool down because you just put in water. and the water is going to heat up because the spoon is going to lose heat, but the water is going to gain heat, which is why it heats up. So there are two ways we can change the temperature of something. The first way is by doing work on the system. So by stirring it up. If we are stirring up something or if we're moving something, we can actually add heat to it. We can heat it up. Hence, if you stir water long enough, it's going to start to heat up. The second way we can change the temperature is by adding or removing heat into the system. Hence, if you have a flame, if you use a flame, you're going to create thermal energy, which is going to transfer into the system. So we have an equation for heat. The equation for heat is Q is equal to mass times the specific heat, which is C, times the change in temperature. That triangle means that's a delta symbol, and that means changing, which means the final temperature minus the initial temperature. All right, so heat is Q is equal to M times C times delta T, and this equation is commonly known as Q equals MCAT. The units of Q are heat is joules. The units of M or mass is kilograms. The units for specific heat capacity, which is C, is joules per kilogram degree Celsius. And delta T is the change in temperature. And the temperature could be in Celsius or Kelvin. And one important number to keep note of is the specific heat of water. So the C for water is 4,186 joules per kilogram degree Celsius. Now let's talk a little bit about specific heat capacity known as C. So when a system absorbs or loses heat, the average kinetic energy of the molecules will change. So the speed of the molecules is going to change when you add or take away heat, thus resulting in a change of temperature if there is no phase change. So specific heat is specifically the amount of heat required to raise the temperature of 1 gram of mass by 1 degree Celsius. So how much heat is required to increase the temperature of 1 gram by 1 degree Celsius? So the quantity of heat required to increase the temperature from T1 to T2 of mass M is directly proportional to the change in temperature. So the quantity of heat is also proportional to the mass of the material. If you're heating up water for tea, you need twice as much heat for 2 cups of tea as for 1 cup if the temperature is the same. The quantity of heat needed also depends on the material. So all this says is that the specific heat depends on the mass, the material, and the change in temperature. Specific heat is an intensive property, and if you remember from quarter one, an intensive property is independent of however much you have. So, in the intensive properties can be used to identify a substance because it doesn't change with the amount you have. So, other intensive properties are boiling point, color, temperature, luster, and hardness. All those things doesn't matter how much of it you have. The boiling point of water is always going to be 100 degrees Celsius. Now, extensive properties depend on the amount that you have. So, extensive properties are the volume, mass, the size, the weight, and the length. So, since specific heat is an intensive property, it's going to be constant for different materials, no matter how much you have. So, the specific heat of water is always going to be 4,186 joules per kilogram degree Celsius. Now here's a table, and if you look at the second column where it says specific heat capacity, it gives you the specific heat of different materials. Now on this chart it says water is 4,100 and 90, they just rounded it up, but the more precise value is 4,186. And what you should know about heat capacities is that if it has a low heat capacity, it has a smaller number, that means that it's going to heat up and cool down quickly. Now, if you have a high heat capacity, so if that number is high, that means it's going to heat up and cool down slowly. So let's look at a few examples. So here's another chart of heat capacities for different materials. So number 1 says which metal will gain heat faster, brass or gold? Take a second to identify those on the chart and find the number for them. So brass is 376, and then gold is 129. Now remember, if it heats up faster, that means it has a low heat capacity. So between those numbers for brass and gold, gold has a lower number, so that means it's going to heat up faster and it's going to cool down faster as well. So the correct answer is gold. Now, number 2 says which metal will cool off slower, copper or iron? So find us those on the chart really quickly. All right, copper is 385 and iron is 450. Now, if it's going to cool off slower, you want a high heat capacity. So between copper and iron, which of those numbers is higher? Iron. And then number 3 says, which substance on the chart has the highest specific heat capacity? If you look at this chart, you should see the highest number is water. All right, now let's jump into some examples of heat transfer using Q equals MCAT equation. So in order to cook pasta, 1.8 kilograms of tap water must first be heated from 24 degrees Celsius to 100 degrees Celsius. How much heat or thermal energy must be added for the water to reach its boiling point? So there's a few things I want you guys to notice in this question. It asks for heat. Anytime a question asks for heat, you know you're going to be looking for Q. It tells us how much water we have, and it tells us the change in temperature. So for this question, we're going to use Q equals MCAT, and we need to know the mass, the specific heat, and the change in temperature. So we always want our mass to be in kilograms, or it could be in grams, but specifically since the specific heat chart gives a specific heat in kilograms, if you look at that chart, under the specific heat column, you see joules per kilogram degree Celsius. It's kilograms. So we want our mass to stay in kilograms. So we have 1.8 for our mass. Now for our specific heat, now the specific heat of water, remember, since we're talking about heating up water, is 4,186. And now, all we need is our change in temperature. Since we go from 24 degrees to 100 degrees, it's our final temperature minus our initial. Our final is 100 and our initial is 24. So it's going to be 100 minus 24. And when we do this, we're going to get our final answer to be 572,645 joules. All right, pretty basic question. All right, number 2. A block of brass is heated from 22 degrees Celsius to 78 degrees Celsius. The mass of the block is 15 kilograms. How much thermal energy or heat must be added to the block of brass for this temperature change? Again, since it asks for heat, we know we have to look for Q. And here's the equation. For mass, which is M, it tells us it's 15 kilograms. For our specific heat, we always have to ask ourselves, which type of material am I dealing with? Now for this question, it says brass. So on my chart, I have to look for the specific heat of brass, and it says it's 376. And then for my change in temperature, I'm going to do 78 minus 22. And when I put all this in my calculator, I'll get 315,840. So, there's a few things I want you to notice about this number. The first is that it's positive. And remember, whenever it's positive, that means we're heating up a system. We're adding heat to it. Now, if this number was negative, that means heat will be coming away from it, which will look like steam. But positive, which means we're adding heat. And then also up in the right hand corner, which is in blue, I have the average amount of heat in a cup of coffee, which is 82,000. So if you look at the answer for this question, 315,840, that's much, much, much bigger than the amount of heat in coffee, which means this is a lot hotter than a cup of coffee. We will need more heat. All right, question 3. How much thermal energy or heat is needed to raise the temperature of 25 kilograms of gold from 45 degrees Celsius up to 80 degrees Celsius? Again, it asks for heat, which is Q equals MCAT. Our mass is 25 kilograms. The specific heat we need is for gold. Gold is 129. And then my change in temperature is 80 degrees minus 40 degrees because it's final temperature minus initial temperature. So 80 minus 45. And then putting all this in our calculators, we'll get 112,875 joules. Go, and as I do this, make sure you put it in your calculator just to make sure you're doing it correctly. Example 4. A 0.550 kilogram block of metal absorbs 4,934 joules of heat when its temperature changes from 20 degrees Celsius to 30 degrees Celsius. Calculate the specific heat of the material. So since this is a heat question, let's start off with this equation. However, this question is a little bit different because we're not looking for the amount of heat required. We're looking for the specific heat of a material. So, if we were to rearrange this equation for specific heat, which is C, we would divide M and delta T on both sides to get this equation. Now we can plug in what we know. Now do we know Q? Yes, we do. It says the heat is 4,934 joules. Do I know the mass? I do, 0.550 kilograms. And do I know the change in temperature? I do. It's 20 degrees to 30 degrees, which is 30 minus 20. And if I put all of this in my calculator, I would get 897 joules per kilogram degree Celsius. Now, if you really want to know what this material was, you can look up what material has this specific heat. And it's not on this chart, but you could figure out which material you were dealing with. All right, example 5. So, an 850 gram block of metal absorbs 5,016 joules of heat when its temperature changes from 77 degrees Celsius to 89 degrees Celsius. Calculate the specific heat of the material. Again, so we're dealing with this equation, and since it asks for specific heat, we have to rearrange it by looking for C by dividing m delta T on both sides. I know Q is 5,016, that's heat. It tells me my mass is 850 grams, but since the chart gives us specific heat in kilograms, we have to change 850 grams to kilograms, which is 0.850. And delta T is 89 minus 77. And when you do this, you'll get that your specific heat is 491.8 joules per kilogram degree Celsius. Last question before we move on to our very last topic for today. So this question says, if 5,000 joules of thermal energy was added to a 100 kilogram block of silver at 45 degrees Celsius, what is the new temperature of the block of silver? So now we're just heating up a block and we want to know what the final temperature is. Again, since this is a heat question, we have to use Q equals MCAT. And then remember that another way to look at this is by writing it like this. Now the reason I want to write it in this way this time is because we're looking for the final temperature. So in order to find the final temperature, we have to rearrange it. Now the first thing we want to do if we want to rearrange this is going to be to divide by MC on both sides. And that's going to get rid of it on the right hand side. The next thing I want to do is add the initial temperature on both sides, which will get rid of the initial temperature on the right side. So my equation for the final temperature will be Q divided by MC plus Ti. Do I know Q in this question? I do, it's 5,000. And I also know my mass, which is 100 kilograms. I know the specific heat of silver by looking at the chart, which is 235. And then I know my initial temperature, which is 45. So if I add 5,000 joules of heat to that block, my final answer is going to be 45.213. All right. Now, notice how the temperature didn't change that much. It changed by 0.2 degrees Celsius, which isn't a big change. So for this, we didn't see a big change. Alright guys, we are almost done. I just want to talk about one more thing to close out the year, which is calorimetry. And specifically, I'm going to be talking about calorimetry without phase change. So all this means is that I'm going to be talking about what happens when we mix substance together and it doesn't change the phase of it. So it's all going to stay a liquid, or it's going to stay whatever state of matter it was in before. Next year in Physics 1, you guys are going to be learning about calorimetry with a phase change. So when you mix things together and things start to freeze and melt and do all that crazy stuff. Alright, so calorimetry means measuring heat. Another device used to measure heat is called a calorimeter. In Chemistry 2 in 2 years, you guys are going to be doing a calorimeter lab. So we will use calorimetry to measure heat when mixing substances. And take note that when something gives away heat, something else gains that heat. So, and when objects are in thermal equilibrium, the final temperatures are the same and the exchange of heat is zero. So for an example, when you put a hot spoon in cold water, like I said before, the cold water is going to gain the heat from the hot spoon, and the hot spoon is going to give away the heat to the water. And then when they eventually become in thermal equilibrium, there will be no heat transfer. So for calorimetry, all you have to do is add up the different heats and they'll equal 0 for when they're in thermal equilibrium. So the heat of the hot spoon plus the heat of the cold water has to add up to 0 when they're in thermal equilibrium. Another way to look at this is that the heat of the cold water is equal to the heat loss of the hot spoon, which is why when I moved the hot spoon to the other side, it became negative. And remember, negative means you give up heat. This also explains why whenever you're holding something cold, eventually it won't feel as cold anymore because your hand and the cold object have reached thermal equilibrium, so they're at the same temperature. Same thing if you're holding something hot. If you're holding something hot, then eventually the hot object in your hand is going to be in thermal equilibrium. All right? And then the last fun fact I want to give you about this is that the only reason something feels cold is because you're giving your heat to that object, so you're losing heat, which is why it's colder, because you're giving up some of your heat. And the reason an object feels hotter is because when you touch that object, it's giving you some of its heat. So remember, heat flows from hot to cold, so hot objects give you heat, which is why they feel hot. So now let's move on to the equation for calorimetry, which is pretty basic. So for calorimetry with no phase change, the equation is the heat of object A plus the heat of object B is equal to 0. So what that means is MCAT for object A plus MCAT for object B is equal to 0. And don't be tripped up because this equation looks a little complicated. It's not that complicated. I just put subscript A and subscript B on the heat equation. So MC delta T, which is TF minus CI for object A, plus M, which is mass for object B, times C, the specific heat of object B, times the final temperature minus the initial temperature of object B is equal to 0. So it's just MCAT plus MCAT equals 0. Let's do an example. And we only have examples 7, 8, 9, and 10 for this. So a 10 kilogram piece of zinc at 21 degrees Celsius is mixed, or it's placed in a container of water. The water has a mass of 20 kilograms and has a temperature of 10 degrees Celsius before the zinc is added. What is the final temperature of the water and the zinc? So I'll put zinc, a piece of zinc, in water at different temperatures. What's going to be the final temperature when they reach thermal equilibrium is what this question's asking. So again, let's start with our basic equation for calorimetry. And I know this is a calorimetry question because it says I'm mixing two substances, zinc and water. All right? Now, let's start with object A, which I'll call zinc. Does it give me the mass of zinc? Yes, 10 kilograms. Does it give me the specific heat of zinc? Well, I have my chart, and the chart says 388. And does it give me the final temperature of zinc? No, because I'm looking for that. I'm looking for the final temperature. And then, does it give me the initial temperature of zinc? Yes, 71 degrees. Now, note in this question, TFA, which is the final temperature of the zinc, and TFB, which is the final temperature of the water, are going to be the same variable, the same thing. Now, let's talk about object B. Does it give me the mass of the object B, which is the water? Yes, 20 kilograms. Do I know the specific heat of water? Yes, it's 4,186. I'm looking for the final temperature of water, and it gives me the initial temperature of water, which is 10 degrees Celsius. And remember, all that's equal to 0. The next thing I want to do is just distribute. So I'm going to do 10 times 388 times TF, which then I'm going to do 10 times 388 times negative 71, which will give me that negative 275,480. And then I'm going to do the same thing for the water. I'm going to do 20 times 4,186 times TF, which gives me 83,720 TF, minus 20 times 4,186 times negative 10. Next, all I'm gonna do is, this is a simple algebra question, combine my like terms. So combine my TFs together, and then I'm just gonna solve for TF. So let me move that constant to the right side of the equation, and then I'm gonna divide to get the TF by itself. And then I'm gonna actually put it in my calculator, and what you'll get is the final temperature of when you mix the zinc in the water is 12.70 degrees Celsius. A fun way you can check your answer is by seeing if your final temperature is in between the two initial temperatures. Because if you mix water at 10 degrees Celsius and zinc at 71 degrees Celsius, your answer shouldn't be lower than 10 or greater than 71. It has to be somewhere in between because you're mixing them. And 12.70 is in between those two. And it's closer to water because remember, it takes a lot of heat to raise the temperature of water. Now moving on to example 8. A 200-gram sample of brass at 100 degrees Celsius is placed in a calorimeter cup that contains 261 grams of water at 20 degrees Celsius. Disregard the absorption of the heat by the cup and calculate the final temperature of the brass in the water. So for this question, I'm mixing brass, I'm mixing water. What's the final temperature when I mix them? Since I'm mixing two things, I'm going to use this equation. Now, object A is going to be the brass, object B is going to be the water. Do I know the mass, the specific heat of the brass? Yes, I do. It tells me I have 0.200 kilograms, no, I changed it to kilograms, of brass. The specific heat of brass is 376. I'm looking for the final temperature, and it tells me the brass is initially at 100 degrees Celsius. Now for the water, which is object B, it says I have 0.261 kilograms of water. The specific heat of water is 4,186. I'm looking for the final temperature, which is TF, and it tells me the water is initially at 20 degrees Celsius. Now all I'm going to do is distribute 0.200 times 376 times TF. Gives me 75.2 TF. Then I'm going to do 0.200 times 376 times negative 100, which is negative 7,520. And that's for the brass. Now let's distribute for the water. When I distribute for the water, I'll get 1,092.55 TF minus 21,850.92. Let's combine the TFs and let's combine the constants, and you should get this. Now, if you move the constant, the 29,370.92 to the right-hand side, you should get this. And then we're going to divide to get the TF by itself. And when you put this in your calculator, your final answer should be 25.15 degrees Celsius. And that's in between 20 degrees Celsius for the water and 100 degrees Celsius for the brass. So I did do this question correctly. And again, the 25 is closer to the 20 degrees, which was the initial temperature of the water, because it takes a lot of heat to raise the temperature of water. All right, example 9. A 150-gram sample of water initially mixed at 45 degrees Celsius is mixed with a 200-gram sample of water initially at 84 degrees Celsius. Find the final temperature of the system. So I'm mixing water with water, but they're at two different temperatures. So since I'm mixing things together, it's a calorimetry problem. Now, for the first water case, the 150 grams, it gives me the mass and the initial temperature. And I know the specific heat of water, which is 4,186. I did change the 150 grams to kilograms, which is 0.150. Now for the second water sample, at 200 grams, I know the same information. The mass is 0.200 kilograms. The specific heat of water is 4,186. I'm looking for the final temperature, and the initial temperature is 84 degrees Celsius. So if I distribute for the first sample of water, you'll get what's in blue. And if you distribute for the second sample of water, you'll get what's in red. If I combine my TFs, since they're like terms, and I combine the constants because they're like terms, I should get this. If I move the 98,580.3 to the right-hand side, I'll have this. Then I'm going to divide the constant over the 1,465.1 and find that my final temperature is 67.29, which that is correct because that's in between 45 and 84 degrees. Now time to move on to the final example. It's the final countdown. So for this question, I have 26 grams of water at 18 degrees Celsius. That's mixed with 49 grams of water at 70 degrees Celsius. Find the final temperature of the water. Same thing, I'm mixing water. The mass of the first sample of water is 0.026 kilograms. The specific heat is 4,186. And the initial temperature of that water is 18 degrees Celsius. For the second case, I have 0.049 kilograms of water. I know the specific heat and I'm looking for the final temperature, but it tells me the initial temperature is 70 degrees. If I distribute the first sample, I'll get what's in blue. And if I distribute the second sample, I'll get that last line right there. Combining like terms, we'll get this. All I did was add the TFs together and add the constant numbers together. I'll move the constant to the right hand side of the equation, and then I will divide by 313.95 to get TF by itself. And what this means is when I put this in my calculator, I'll get my final temperature to be 51.97 degrees Celsius. And that is the end of the last topic. Now, I'm going to do a summary really quickly, but before I get to that, next year when you guys relearn this in Physics 1, you're not only going to be solving for the final temperature when you mix two things together, but it could give you the final temperature and it will ask you to solve for the specific heat of object A or the specific heat of object B. Or it can ask you to find the mass of object A or the mass of object B. Or the initial temperature of object A or the initial temperature of object B. Just know that there are different calorimetry type questions that they can ask you, but for this year, since it's our first time learning about this, I'm going to keep it simple and we're just going to learn about how to find the final temperature when we mix things together. So let's go over a summary real quickly. We started off today learning about the laws of thermodynamics. There's 4 of them: the 0th law, the 1st law, the 2nd law, and the 3rd law. Don't ask me why it starts with the 0th law, but scientists decided to do that. The 0th law said that things in thermal equilibrium have the same temperature. The 1st law said that energy is conserved and cannot be created nor destroyed, only transferred. The 2nd law says that heat goes from hot to cold. And the 3rd law says as you approach absolute zero, this order approaches a constant value. And that's just a fancy way of saying that the lowest temperature that we can reach in the universe is 0 degrees Kelvin. After we talked about the laws of thermodynamics, we talked about how to convert between temperatures. And I have those equations at the bottom. And then we talked about the difference between temperature and heat. Temperature is the quantitative description of how hot or how cold something is. Hotter objects have molecules that move faster. Colder objects have molecules that move slower. And heat is the transfer of thermal energy from one place to another place because of a temperature difference. If heat is positive, you're adding heat into the system, which is known as being endothermic. And if heat is negative, that means heat's leaving the system, which is exothermic. Remember, exo means to leave. That's why it's called things are called an exit by the door, because you leave. So exothermic means that heat is leaving and it's negative. The units of heat are joules, and then the equation for heat is Q is equal to MCAT. So M is mass, C is specific heat, and delta T is the change in temperature. And I don't care if the change in temperature is Celsius or Kelvin, because it's a change. Calorimetry, and then we ended with calorimetry, which we use to measure the heat when we mix things together. So when something gives away heat, something else has to gain it. And when objects are in thermal equilibrium, the final temperatures are the same and the exchange of heat is zero. And for calorimetry questions where there's no phase change, we do QA plus QB is equal to 0, which is MCAT plus MCAT is equal to 0. Now, if you guys are still a little bit confused after this lesson, because it was a lot to digest, here's a YouTube video for you to watch. So go ahead and watch this, but also if you type in heat or heat in chemistry or calorimetry, no phase change into YouTube, other videos will pop up. Also, feel free to email me. And feel free to just email me anytime, even over the summer, if you guys have questions. It was an honor to teach you guys. I love all of you, and I cannot wait to see you all again. All right, see you guys. Water has a much higher specific heat. Also, guys, before I continue, specific heat and heat capacity are interchangeable terms, so they mean the same thing. So water has a much higher specific heat than the glass or metal used to make cookware. This helps explain why it takes several minutes for water to boil on a stove, even though the pot or the kettle reaches a high temperature very quickly. Now, let's get an overview of this very amazing year. So, when you guys were little chemistry babies, when you first came into my class in the fall, we started with a unit called matter. And in matter is where we basically learn how to classify matter, how to calculate density, and learn about physical versus chemical properties and changes. So how do we describe matter? And then we moved on to atoms. So matter is made up of atoms. So we talked about the atomic theory and how atoms have protons, neutrons, and electrons, and we learned how to calculate those numbers. And then we talked about what happens when you have the same number of protons but different numbers of neutrons, which led to isotopes. And then we started talking about how, these electrons start moving around in that atom. So how they're in different orbitals and how they have different electron configurations. And based on where the protons, electrons, and neutrons are, you have different periodic trends such as electronegativity and ionization energy. And then once we talked about, atoms and how we have protons, neutrons, and electrons, we moved on to nuclear chemistry. So what happens when, you start to break these atoms apart and you start giving off protons, giving off electrons, and then how to calculate when these atoms start to decay and how much are we going to have after a certain time period. And then we moved on to the actual chemistry part of the class, where we talked about chemical bonding. And you guys learned about the two major types of bonds, ionic bonds and covalent bonds. And you learned how to name ionic compounds, how to name covalent compounds, and how to make Lewis dot structures for ionic and covalent compounds. But not only did you learn how to do Lewis dot structures, you learned about the different geometries. So we talked about electron geometry and we talked about molecular geometry. And remember, with molecular geometry, that's where we really find out, how does lone pairs bend and make different funny shapes of the molecule. And we learned about the octet rule and different exceptions to the octet rule. Now, when you guys do get to chemistry 2, you're going to be talking about more types of bonds because we have hydrogen bonds, we have metallic bonds, we have polar bonds. So you're going to be learning all about that in chemistry 2 when you're a senior. So after talking about ionic and covalent bonds, we start talking about chemical solutions. So now that's when we really start to get liquids and aqueous solutions. So we talked about how to go from grams to moles to particles to volumes of gas. We learned how to do molarity and concentration, where you guys had that pretty fun lab quiz. And then we finished off with solution dilutions, which was the equation M1V1 equals M2V2. And then after chemical solutions, we were on probably your favorite unit in chemistry, which was chemical reactions, where we talked about what happens when we start mixing chemicals together. And first, when we mix chemicals together, is it going to dissolve in water or are we going to get a solid? So is it soluble or non-soluble? And we talked about 5 major types of reactions, which were double replacement, single replacement, combustion, synthesis, and decomposition. And after learning the different types of reactions, we learn how to balance chemical reactions, where we put the coefficients in front. And this was very important because this was the segue into our next unit on stoichiometry, where we looked at these coefficients in the front and we learned about mole ratio, but we were able to find the limiting reactant, the excess reactant, the percent yield. And we finished off stoichiometry with calculating the empirical and the molecular formulas given experimental data. So if I have a certain percentage of an element in a compound, how do I find out the formula of it? And then the last hardest topic we talked about was equilibrium reactions. So up until this point in chemistry, we talked about what happens when a reaction goes one way. So we did a unit where we talk about equilibrium and what happens when a reaction can go forwards or can go backwards. And you guys might have thought this unit was hard, but don't worry, because you're going to revisit it in chemistry too. So you're going to be seeing it for a second time. And hopefully by that time, it'll click even more. And then last week, we talked about gases and the 4 basic gas laws, Boyle's law, Charles's law, Avogadro's law, and Gay-Lussac's law. But we also talked about the ideal gas law and the combined gas law. And this week, Unit 10, our very last unit, we're going to be talking about thermodynamics. And we're going to be talking about the 4 laws of thermo. We're going to be talking about what heat is. And we're going to be talking about calorimetry. Now, you guys probably don't know what calorimetry is, but you will by the end of this lesson. Moreover, next year in Physics 1, you guys are going to be spending a few weeks in the thermodynamics unit. So you're really going to be unpacking it even more. But this is going to be a good prep for it because next year you guys are going to have to build solar ovens in that class during the thermodynamics unit. So, give yourselves a pat on the back. I'm super, super proud of you guys. I know that I pushed you guys a lot, but you rose to the occasion. And with that being said, a lot of you guys will be doing Honors Physics 1 next year. So, be proud of yourselves.